Good morning to all of you. I am Priyotma from EEB department. So I, along with my team members whose name are Palak Gupta, Naman Gupta and Rashmi Rani, together here to present our presentation over the topic recent innovations in our EEE department. Well, my topic is optical communication satellite. So before explaining my topic, I would like to say some lines about my department, that is electrical department. So well, electrical engineers are nowadays forefront of all the most important innovations taking place in this world. Whether working for the private sector, to the government sector or major research institutes, the electrical engineers are always pushing the boundaries of all the possible. Well, recently they have contributed huge to our society. Well, all we know that Michael Faraday is known as the father of our electrical engineering. So as I have already told about my topic, that is optical communication satellite, before coming to the broad brief description, I would like to define optical and satellite communication. Well, optical communication, the use of electromagnetic waves in the region of the spectrum near visible light for transmission of signal representing speech, pictures, data pulse or other information, usually in the form of laser beam modulated by information signal. This is what the optical communication was. Now coming to the satellite communications. So satellite communications using an active or passive satellite to extend the range of radio, television or other electronic transmission by returning signals to Earth from an orbiting satellites. Now this all was only the definitions of optical and communication satellite. Now coming to the introduction part, I would like to explain my topic, that is satellites. Well, satellites are specifically made for telecommunication purpose and they are used for mobile applications such as communication to ships, vehicles, planes and handheld terminals and for TV and radio broadcastings. The power and bandwidth of these satellites depend upon the preferred size of the footprint, complexity of traffic, control protocol schemes and the cost of ground stations. A satellite work more efficiently when the transmissions are focused with a desired area. Satellite should be designed by keeping in mind its usability for short and long-term effects throughout its lifetime. And it is, I can say, the most important point, that is we should keep its position in our mind, like its angle, its length, its breadth, its area, everything should be in your mind, that Earth station should be in a position to control the satellite. This is the most efficient thing which one should keep in its mind. Now coming to the basics, like introduction was done and now it's the time to know the basics of our satellite communications. So basically satellites orbit around the Earth, as we all know. So depending on the application, these orbits can be circular or elliptical. Depending on the demand, depending on the utilizability, these orbits can be either circular or elliptical. Satellites in circular orbit always keep the same distance to the Earth's surface following a simple law. The attractive force, which we are representing here using capital F and small g of the Earth due to gravity, equals m dot g capital R upon small r whole square. And the next point is centrifugal force, that is we are representing here with the help of capital F and a small c, trying to pull the satellite away, equals m dot r dot omega square. The next thing is, here we are using m, and m is representing the mass of satellite, and capital R, with the help of capital R we are representing here the radius of Earth, and small r is basically the distance between the satellite to the center of mass, and small g is the center of gravity, and omega is the angular velocity whose magnitude is equals to 2 pi f, and f is where the frequency of the rotation. So these were all the basic facts that we should know about satellites. Now talking to the Now I would like to call my acquaintance Palak Gupta to describe the further slides. Thank you.
Hello everyone, my name is Palak Gupta and I am from Triple EB. Now I am going to start my further presentation which is already initiated by my other group member. Let's start the presentation. Our first slide is application of satellite and their subtopics are weather forecasting, radio and TV broadcasting, military satellite, navigation satellite, global telephone, global mobile connection, and the pictures related to the application of satellites are this is the first picture, this is the second one, and this is the third one, which is navigation satellite. Our next slide is frequency allocation for satellite. There are two subtopics. First one is navigation satellite services, which include the global positioning system. Second one is meteorological satellite service. They are often used to perform search and rescue the service. Our next slide is types of satellite based on orbits. The first one is geostationary Earth orbit. Second one is low stationary Earth orbit. Third one is medium Earth orbit. The pictures are this. In this picture, how the satellite work, it shows types of satellite and the images of that satellites are this. Now I would like to call my friend Naman Gupta to describe further slide. Thank you.
I am Naman Gupta from Triple EB department. Today I am here to express my views on types of satellites. Here we start. There are three types of satellites. First, satellite communications. The second, military satellites. And third, weather satellite. Link design, wavelength and polarization. The transmit and receive beams inside the terminal are arranged to have orthogonal linear polarization and separated in the wavelength. This enables the same telescope and pointing system to be used for both transmit and receive beams, since the optical duplexes scheme can be used. Circular polarization is used over the link so that the received power does not depend upon the orientation of the satellite. Second, link budgets for an asymmetric link. The requirement to transmit a much higher data rate on the return link than on the forward link implies that the minimum configuration is one with a large telescope. We have to decrease our losses, so we used LEO telescope. A smaller telescope at LEO has the disadvantages of to reduce light collection hurt, the advantages of reduced pointing loss due to wider beam width, and that's how our losses will be reduced, and that's it. Third, pointing acquisition and tracking. Pointing. This term depends on accuracy. Accuracy to which one satellite knows the location of the other. Accuracy to which it knows its own attitude and accuracy. Acquisition. This enables the user terminal to log the beacon and transmit its communication beam back along the same path. So our communication will directly come to our machines, and then the communication converts to our media, and that's it. Third, tracking. After successful acquisition of GEO and LEO terminals are operating in tracking mode in the mode on the board disturbance, which introduce pointing filter into the communication beam, are alternative means of a fine pointing control loop enable to acceptive communication to be obtained. Point ahead. This is needed because of the relative orbital motion between the satellite, which call for the transmitted beam point in a space where the receiving terminals will be at the time of arrival of the beam. Here is the block diagram of a generic direction optical terminal is shown. Here we can see user subsystem, and the signal goes to point ahead assembly, and their duplexers and quarter wave place, fine painting assembly and telescope. The signal will come from user subsystem, and there it goes from there to telescope, and then telescope send the signals to last slide. Optical antenna. The optical antenna comprises the telescope and the force pointing assembly. The telescope is a refractive capillary design which does not have the secondary mirror. Spur gear and the planetary gear, the total height of the CPA above the platform, which affects the LEO and GEO link absorption by solar arrays, antennas and other spacecraft appendages. Integrated transmitters. This consists of a prime reducement pair of a laser modules, a rudimentary switch and a point ahead assembly. The lasers are connected in the PM by a signal mode polarization. This allows greater layout flexibility of the optical bench and simplifies the redundancy switching. Each laser module contains a laser diode for lighting lenses, cylindrical lens and focusing lens. For coupling light into the fiber, coupling efficiency into the fiber is accepted to the exceed 70%. Fine pointing loop. The fine pointing loop is required to attenuate external pointing disturbance so that the residual mispoint angle is a small fraction of the optical beam width. The closed loop tracking subsystem consists of a tracking sensor which is determine the direction of the incoming communication beam with the angular resolution around 5% of the optical beam with the fine pointing mirror assembly with compensates beam mispointing effects. Optical bench. The diplexer quarter wave plate at the other lens system required to actuation tracking are placed in an optical bench. Optical bench, the diplexer has a dielectric multi-layer coating which provides effective transmission of one type polarized light at the transmit wavelength and rejects another type of polarized light at the receive wavelength 800 nanometer. I repeat, 800 nanometer. The transmit light to circular polarization state prior into the telescope, the PAA lasers and the redundancy switching mechanism on the other side, while the diplexer receive perhaps paths and the calibration path are on the other side of the optical bench. Structural configuration. The SWOT has a novel structural of the thermal design which satisfy the unique demands imposed by the various subsystems. The main structural elements are a truss frame assembly which supports the optical the orthogonal to the optical bench. Key design drives for the structure are the optical bench, pointing stability, soft mount, conforms and base bending. Base bending is important, and the height of the terminal above the spacecraft depends upon the height of the terminal craft and mounting on deployment mechanism. The head unit occupies an area of about 40 by 40 centimeter depending upon the platform interface. Advantages. Optical technology offers a number of potential advantages over microwave. The antenna can be much smaller. A typical microwave dish is around 1 to 2 meter across the required deployment in the orbit. An optical antenna occupies much less spacecraft regal, instead having a diameter of the range 5 to 30 centimeter, therefore easier to accommodate and deploy. Optical beam widths are much less and microwave leading to very high antenna gains. Both transmit and receive. This is enabled to low transmission and power to be used leading to a low mass, low power terminal. It also makes the optical beam hard to interpret and fan leading to convert features of military applications. Consequently, there is a major effort underway in Europe, USA and Japan to design and fight quality optical terminal. Conclusion. Optical satellite communication promises to become an important element in future space infrastructure and considerable development. A factor is currently underway in Europe and elsewhere. So here is the conclusion of our presentation. Thank you so much, and I would like to thank Ms. Deepti Gupta ma'am who gives us such an interesting work in that lockdown period where we all are getting bored.